Hello there. In this video, I want to calculate the moment of inertia of a uniform ring. This is going to be a nice and easy calculation, right? It's just a simple, linear, infinitely thin hoop here with the axis passing straight through the center of the hoop. We're going to calculate this with the definition of moment of inertia. This is going to be a useful derived result for further videos as we build up more complicated objects. But let's go ahead and get started. Right, so as usual, we're going to start by labeling one of our infinitesimal mass elements. So this little infinitesimal mass element is going to have some dm, and it's going to occupy some infinitesimal linear spatial element, which I'll call dl, right? And of course, it's going to be located some distance away from the axis of rotation, which I'll go ahead and, just like in previous videos, call gamma. And so we know that the moment of inertia of my ring is defined as the integral over my ring of gamma squared dm, right? Immediately, we can trivially see that gamma and r are, well, equal. The distance from my axis of rotation, of course, for a circular ring is just the radius of that ring. Cool. Uh, Now dm is going to be equal to, just as usual, lambda, where lambda is the linear mass density, times dl, right? Just take your linear mass density, multiply by our little infinitesimal length elements, and that's going to give you the little infinitesimal mass. Beautiful. Let's go ahead and note what lambda is going to be equal to, right? If we have a uniform ring, lambda is just going to be equal to the mass of my hoop m divided by, right, the circumference, because it's an infinitely thin ring. So we take the mass, divide by the circumference. What's the circumference of my ring? Oh, that is just 2 pi r. Awesome. Let's go ahead and make our substitutions. So we have I of ring is going to be equal to the integral, and I'll still say over ring for now, of r squared times lambda times dl. Yeah, and I'll sub in for lambda later on. That's fine. Cool. So the next thing we need to ask is, what is this dl? What is this linear spatial element? And we need to define that more robustly, more rigorously with an actual coordinate system. And let's go ahead and use polar coordinates because we just have a nice circle here. So I can mark the location of any one of my elements on this ring with two key locations. The first is with some radius, and they're all going to be at some fixed radius r. Let's go ahead and just replace this gamma here with r, since we know that, in reality, these are, you know, gamma is equal to r, as I noted up there, right? And then this is also going to be at some location phi, or at some angle phi. So let's go ahead and think about what this linear element dl is actually going to end up being. Well, so let's mark two endpoints kind of this linear element here, and we can see that what we're going to kind of have here is a little sector. And let's blow this sector up. So we're going to zoom in on this. So here we go. I'm going to put my 2 points down, and we have like a little infinitesimal arc here, right? And here's like the center of my circle right here. Or I'll do it in red to kind of match the picture that we have up here, right? So here's my little arc. And then both of these are R, right? This radius R away from my arc. And what's the angle between them? Well, if it's an infinitesimal arc, right, then we have some angle of d phi between them, right? Or we have some delta phi, some angle between them that limits down, right? The limit as delta phi kind of runs towards zero. And so if we have this little picture, what's that arc going to be, right? This guy here, this is dl. So dl is simply going to be equal to r d phi. We're just going to use a arc length formula. Beautiful. Okay, so we can just substitute that in for dl, and now we have an angle which we can actually integrate over. Beautiful. So we're going to have that the moment of my inertia of the ring is equal to integral r squared lambda dl, which is equal to the integral of r cubed lambda d phi. And where's this going to range from? Well, I know that phi for a ring, if I go ahead and start at phi equal to 0, and I go around the entire ring, that is a terrible arrow. Something like this, right? We go around the entire ring. We have 2 pi radians in a circle, right? So we start here, we end here. Phi equal to 2 pi. Beautiful. We just traverse the entire circle. I can leave that there. Okay, so phi is going to range from 0 to 2 pi. Cool. Look at that. There's no dependence on phi anywhere in this integral. So this is just going to result in a multiplicative factor of r cubed lambda times 2 pi when we actually go and do that integral. All right, let's go ahead and substitute in for lambda. Lambda is going to be equal to, as we said before, or here we go, I'll just drag this over in for lambda. So we have r cubed times m over 2 pi r times 2 pi. Cancel, cancel, cancel out there, and we get that the moment of inertia of my ring is equal to mr squared. Awesome. This result is going to be very, very useful in constructing, other objects like spherical shells and things like that in future videos. So this is a really useful result.